has been working since some time, I guess, about some fluid gravity correspondence. Please.
Thank you, and thanks everyone for coming. This, as you'll see, is a talk that has multiple angles. I don't necessarily plan or want to cover everything, so just stop me whenever. We can go on a tangent at any given point. So as a joke, let me start with a question, because it's very common to talk nowadays about conspiracy theories, so I'm going to put one out. How many of you have taken a formal course in fluid dynamics? Raise your hand. 1, 2, 3. So it's not a majority. So my conspiracy theory, which is, I really intend as a joke, is a conspiracy theory by the body of physics branches to not think about fluid dynamics. Because fluid dynamics, I would argue, is the only field that cannot get by perturbing a particular state. We cannot rely on just take the harmonic oscillator. We're going to do a little bit and gain quite a bit of traction. We cannot take a special solution, perturb it a little bit, and then know something about it. It's the only field of physics, I would argue, at least in classical physics, where the nonlinearity has to be embraced. And I think for the longest time, especially, well, in all branches, but in particular in general relativity, we have been getting by trying to get a lot of information from the theory without ever embracing its nonlinearities. And we've done it in 2 different ways to avoid it. One is to look for very particular solutions. Einstein's equations are extremely complicated. You find a few ones, and then you do perturbative analysis over top of them. Or you use the power of geometry, and then you can prove things like the singularity theorems by Penrose and Hawking that are tremendously powerful. It tells us what is going to happen in the future without ever telling us the details of how we're going to get there. But you can get a lot of bang for your buck. However, as we move to the 2nd century of the theory, I think we need to embrace it. And there are some interesting things that I claim, of course, we need to understand. So why do I care about coming? Oops. Why this? I cannot move. OK. Why do I even have the right to think about fluid dynamics? Let me show you 2 movies. One is a black hole. The other one is saliva. So the left-hand side is a black hole in higher dimensions. It happens to have an instability, a long wavelength instability, that makes this black hole shrink in some areas while it's elongating, and then makes bulges on some other areas. This is, on the right-hand side, you have a typical instability of, again, long wavelength fluid. This is known as a Rayleigh-Plateau instability. This is something you can do with your fingers. And there is a significant, at least qualitative analogy in the two cases.
I got missed something. A black hole having an instability?
Yes, it's 5 dimensions. This is a black string. So we're in 5D. In 5D, we don't necessarily have any of the theorems that we have in 4D. And in fact, I would argue we still don't have all the theorems in 4D. But yes, this is known as a Gregorian-Laflamme instability. And you can heuristically think about it as if you have a bunch of mass m, and you're going to distribute it in a cylinder versus a sphere. If the cylinder is sufficiently short, it has more entropy than the same mass put in a sphere. But if it is sufficiently long, it doesn't have it, and it wants to go into the more entropic solution, and that's the one on the left-hand side that wants to eventually pinch off and form single black holes that will join to form a larger one. So this has been understood for a long time. This on the left-hand side was a simulation that Franz Pretorius and I did a long time ago, which was to try and understand what the end state of the instability was. I mean, people have done, as I said at the very beginning, Gregory and Laflamme, have taken these solutions and found that if the extra dimension was sufficiently low, there is an instability, but we didn't know what the final state is or was until this simulation came along. And that simulation, of course, requires solving Einstein's equations in full generality. But of course, there is so much you can do with simulations. Simulations, every time you do one, you get one solution. The ideal simulations are those you can kind of out of not only perhaps answer some questions, but maybe open some new avenues of research and point to perhaps what is a better way of understanding the system in analytical means. So the motivation of my talk, or what I've been doing for a very long time, is to gain a better and different perhaps understanding of gravity in the nonlinear dynamical regime. In particular, I'd like to understand when nonlinearity is transitioned in the case of waveforms. So one very, I don't know, one very interesting behavior that we saw first theoretically when the solutions of binary black hole problems was obtained, and then in the data or gravitational wave detections, is that you have early on two objects, and this is something that Ricardo does for living, or part of his living, is to try and estimate with kind of perturbative arguments what's the early behavior of two objects that are coming together, and then you have this kind of sinusoidal shape that increases in both amplitude and frequency. Eventually they come together and they merge, and if you wait some time, and not long, then it decays away to a black hole that is described by the Kerr solution. And if someone were to press you to say, what's going on? In the merger, this is the most nonlinear regime we can think of nature. There's two black holes of the same order hitting each other at about a large fraction of the speed of light, and we have such a silly-looking waveform. I mean, you perhaps would have expected, all the fireworks just turning on, and this is just very mundane. Why? I don't know why, and I'm going to tell you, perhaps, and this is something I've said in the past in some talks here, a kind of a crazy idea. But in hydrodynamics, we do know something where in some regimes, something shows a very complicated features, and in others, it's extremely simple, though damning, and that's the formation of hurricanes. I didn't pause for particular reasons, but in the formation of hurricanes, it's a turbulent behavior, but it's a turbulent behavior that is there because the height of the atmosphere at some point becomes irrelevant with respect to the latitude and longitude scales. The typical image we have in fluids of turbulence is if we steer a fluid, it will generate vortices, the vortices will break, and they will continually go to shorter and shorter scales so the energy they have gets dissipated away in the viscous scale. But if you do the same thing in 2 dimensions, 2 plus 1 dimensions, or in 3 plus 1 dimensions, however many dimensions where everything but 2 dimensions are relevant, energy wants to go in the opposite direction. There is a quantity called entropy that is related to the vorticity of the fluid flow, which bounds the way energy can move either to the UV or the IR. And in the 2 plus 1, it's a quasi-conserved quantity. It's a quantity that varies much more slowly than any other quantity that one can compute that is dynamical. And it's the one that basically puts the damper, and it says, energy, don't go to the UV, go to the IR. And this is why we believe we have hurricanes. This is something that, as I said, happens in 2 plus 1 hydrodynamics. That's not happening in 3 plus 1, and maybe there is a connection with gravity, and we'll get to talk about that. So a few things I'll say. Well, we'll review this zoo of options for gravity, and then slowly we'll try and connect with hydrodynamics. We're going to do some intrinsic connections between hydro and implications for gravity. And then slowly we're going to try and explore this nonlinear regime. If you haven't been paying attention, at this current stage, there's a significant tension going on in the field of gravitational waves. And I'll explain what the tension is. Suppose you are a gravitational wave detector, detecting analyst, and then you see this waveform, and then you see this thing coming down. I told you that we know how to do perturbations, say Kerr plus perturbations. So this is a linear problem that assumes the solution, the state of the system, can be well described by an unchanging Kerr with the perturbations on top of it that is non-back reacting. Out of these, you can find special solutions known as quasi-normal modes. And they're quasi because they're not normal mode. Energy can leak out of the system, either radiated to infinity or falling into the black hole. And as a result, these are modes that oscillate with frequency, say omega real, but there is a decay associated to it that is omega I. And what we know in general relativity is that these two numbers are uniquely determined by the mass and the spin of the system. So if you measure one mode, out of one mode you can get mass and spin. If you measure 2 modes, then you have a pretty strong test of general relativity. If things are not consistent, you can go and claim there is something funny going on. The problem is when can you regard a system to be behaving linearly? you have a nonlinear theory, when can make this assumption be made safely? If you wait long enough and you do it from here over, the signal has become so weak that it's hard to detect and do anything with it. If you start climbing to the left as much as you can, well, maybe at some point you get affected by nonlinear features, and you may conclude that there is a different general relativity which is not there. It was just fakely introduced by an overly eager group of people that is trying to extract a linear behavior in the nonlinear regime. And nowadays, if you look, there is a significant kind of back and forth in between this. Of course, there is a very strong bias to want to see this, because if you maybe are the one that claims that it's true, and then you can show evidence that, yes, you have just measured two modes, maybe there is a significant price at the end of that story. And some of us says that's nonsense, and so here is the fight. But I'm not going to go into that unless someone asks me any further. But so why do I want to go to fluid gravity correspondence? And then I'm going to tell you a long story, a story that started in the 80s by Thibaut Damour. So Thibaut, this is the 80s. We still didn't understand much of what to expect from the theory. And what people were trying to do is just see potential connections with other fields of physics where we thought we understood things better. So Thibaut said, well, let's take Einstein's equation and project them on the horizon. If you do that, I'll show you the equations later, you end up with two equations. One that is a celebrated Ricciardouri equations. This is at the very core of the singularity theorems. It's something that tells you if you initially start convergent in general relativity, you have no choice but to eventually converge to a singularity, for instance. So this is just saying that. There is an equation of motion that tells us that the null surface will behave in a particular way. And this null surface might expand all the way to infinity, might collapse to a singularity, or might be such that as you wait long enough, it just stops expanding. And when it does stop expanding, if you wait forever, that region defines a black hole. There are equations people didn't understand at all. It was very complicated. And so then they took a different route, which is to take this surface. Now, I mean, part of the reason why this equation is complicated is that's a null surface. A null surface in a pseudo-Riemannian metric is a singular surface. It's difficult to compute things there. You have to be very careful, and there is a lot of gauge ambiguities that come in. So then other people, and this came on the so-called membrane paradigm, decided to put a time-like surface around the black hole. So it's something that is very close to the black hole, but it actually has some net acceleration so that it never becomes null. And when you do that, you project Einstein's equation, and lo and behold, Einstein's equations can either be cast in terms of Navier-Stokes hydrodynamics, or it can be cast in terms of electrodynamics. So there was a very quick connection to something we knew. And out of that, a lot of things came out. In particular, the very basic understanding of how a black hole powers a jet comes out from that very calculation, because one of the things you can compute is what is the resistance of vacuum. Vacuum seems to have a resistance in this picture. There is also, we know from rotating black holes, the work of Penrose, that we can extract energy. You put all those things together, and very rapidly you get the so-called Blandford-Snag mechanism to power jets from black holes. And essentially, that stayed there for a very long time. Why? It's because, well, you could make these connections in this surface. No one defines this surface in a unique way. I could choose a surface. Someone else can choose a surface that is very close by, but it has a wiggle. And what one will claim there is physics, the other one will say, wait a minute, I don't see the same thing you do. So it got resurrected in the mid-2000s when people motivated strongly by holography said, wait a minute, there is a special surface, at least in the context of anti-de Sitter, which is the asymptotic boundary of the anti-de Sitter. So there is a case where you put your gravity interacting with a negative cosmological constant, and there is this funny business in which infinity is not that far. You can interact with infinity, you throw something, a ball will be, if I throw a ball to infinity, it will eventually come hit me. Because that surface is unique in more than one way, one can say, let's redo the calculation. Let's take Einstein's equation and project it there. the important thing I want to also say here is the people that did this came from a different corner. They didn't come from general relativity, they came from field theory in some sense, or string theory, and they come with a completely different tool set, which in some cases is very useful, in some cases maybe it's hindering, but in this case was very useful. Coming from a field theory point of view, they wanted to say, well, maybe what we can do is just do recasting, but it's a recasting of the equations that is in a way that is aware of the wavelengths that we're talking about. So they introduce a gradient expansion. And this is a very important difference. A general relativist, like here, would say, I want to study perturbations, and I'm going to do something of the form. So I'm going to postulate that my metric is the curve metric plus H1 plus H2, etc. If I imagine epsilon governing the size of my perturbation, this would be order 1, this would be order 2, etc. These guys come in a very different way. They said, well, I want to think of this as G curve that depends on the mass and depends on the spin. But we're going to force a perturbation by promoting these guys to functions, let's say, such that in a gradient expansion, the leading order contribution of m is a constant, which we're going to call mass. It's a spin, which we're going to call spin. But they all will have a small variation, such that the derivative of any field, either m or a, is such that it's subleading in gradient. And then you can recast the perturbations, and then you have a different type of structure. And this is non-trivial, so let me just make a side comment here. So let's go back to Navier-Stokes, and let's say in the implicit case, in the incompressible case. So the equations are more or less of this form. And now I can imagine saying, well, let's do a perturbation theory associated to this. I can do I can follow two paths. One is a gradient path, where I'm going to say something like that. Higher derivatives are subleading with respect to lower derivatives. If I do that and I look at this equation, the first term I'm going to throw out is that one. Because this will have the highest derivative. This first derivative is two derivatives. But if I throw out this and I try to analyze what is the associated Reynolds number of this system, it's infinite. So any mode will be turbulent. So all turbulent. I can do another one, which is perturbation in the size or the amplitude. So here I can imagine that my background flow is a constant velocity, let's say. And then I look for a small variation. And when I do that, this survives, that survives, and there is no relevant piece coming from here. It's just an advection. So in that case, all decay. And this underlines the reason why I try never work in perturbation theory. So when I work with Ricardo, I'm getting very confused. That's just my limitation. Because I mean, perturbation theories are extremely dangerous to me. They're very good at getting some particular answers, and they're very good at missing some others. And in some sense, one slightly puts the answer, not the most likely answer by the scheme of perturbations that one adopted. And in order to see a more general thing, one has to carry the perturbation scheme to much higher orders, resum, and see if there is something else. So there's nothing wrong with carrying this program or that program to higher orders. And then, in this case, one begins to say, oh, there is something that seems to be taking energy away, which is what this term is trying to do. And on this case, when one carries to sufficiently high orders, begin to see that there is some nonlinear coupling that will do something interesting. So that's the reason why I said, I'm not smart enough to do perturbations, I'm going to do numerical simulation. But let's say, suppose you get, and then we're going to discuss, oh, it also works here. Amazing. I thought I had to point here. So this is something you would obtain, and then we're going to say a few more words in a second, if you're not asymptotically anti de Sitter. There are calculations you can do on this surface that we would all agree would be at, and very interesting results came out. But anticipating what I was going to say later, at the end of the day, we really want to throw out the negative cosmological constant. At the very least, we know we don't live a universe where the cosmological constant is negative. We know we can kind of get away with assuming lambda equals to 0 for some things, but definitely we would like to go to a more general case. So anything that depends strongly on having a negative cosmological constant is suspect from the get-go. So then one would say, well, what can we do? Let's not choose this surface. Maybe we won't consider going back to the null surface, because we already argue that any time-like surface in between is arbitrary. And so this is kind of the new era of this fluidic gravity correspondence, and this comes into work that is was started in the 20s by people like Laura Donnet, Marteau, and a whole bunch of other people that have recognized some new structure that was there from the very beginning, but only recently people were kind of recognize it's there and beginning to ask questions. So I'll describe some of these things. Yeah.
When I start getting turbulence, do I throw away the equations, or are the equations still okay?
No, the equations are still okay. What you begin to lose is the ability to compute. So then, okay, how do you? First, the equations are still are nice equations. They are hyperbolic. They are well behaved. Of course, you can have crossings. There, you have to impose some further conditions. That the unique solution you're going to pick as a physical one is the one that maximizes the entropy change. And then you can keep going. But what happens is now two solutions that are, or two initial configurations that are very close to each other begin to differ significantly in a controlled way, but you can still evolve through.
No, but my question is not about the equation itself. If I define the equation as saying this is my equation and I don't touch it anymore, but rather from an effective theory point of view, we know that there are higher curvatures, right? Higher viscosities in this case that we are throwing away. My question is, when turbulence kicks in, are all those terms important, and therefore this equation might be well defined, but it will be useless to predict the water behavior, or is it still useful?
It depends on the regime you are. So like if you are in 2+1, where energy is going significantly out in the other direction, turbulence does give this kind of energy exchange that wants to go to the IR instead of the UV, and that's perfectly fine, right?
Okay.
In the other case, okay, there is some missing physics. You can still keep using it. So now what you're saying in this, there are multiple answers to your questions, not all consistent with each other. So let me try to give you all of them. So one is, as you go to shorter and shorter scales, these viscous terms, what are they doing? They're accounting for that physics that you're not incorporating because now you're beginning to probe molecular dynamics. And you say energy that gets there gets thrown away. So you're not capturing it. So to the extent that you say, this is reasonable for me, okay, that's fine for you. But it's uncertain, right, at the onset. But yeah, so you could say, okay, that's the physics, and I'm willing to live with energy not being conserved, and I'm going to go through with it.
Okay.
So
then probably I can only trust the equations for a very short time after turbulence kicks in, right?
No,
Because eventually those effects that I'm modeling phenomenologically, it will start depending on the details of that modeling, and then I will not be able to predict the behavior.
That's right. So this is why in front of the viscous term, there is something that is the measure of your ignorance, or our ignorance, which is the transport coefficient, and we put a larger number for honey than they put for water, right? So the ones that the case takes energy more rapidly than that. That's the effective number that is trying to capture that physics that you don't have, and yeah, in many regimes, that's good enough.
Okay, thank you.
Okay, so where are we now? So suppose you buy, and I'll tell you a few more words here, that we're trying to build a tighter and tighter connection between hydro and gravity. So I'm going to revisit a little bit, starting first this hydro correspondence, fluid gravity correspondence between gravity and what you were asking earlier, the ADS boundary. So circa, oops, that was bad. Okay, I don't know what I'm doing now. Yeah, so for the longest time, people were saying, wait a minute, how can there be a connection between hydrodynamics and general relativity? Hydrodynamics generically develop shocks. Even out of smooth initial data, I will have shocks just because the velocity of propagations or perturbation at different points of the fluid will be different. And so at some point, we'll either hit each other or begin to kind of backweight the fluid. And again, we experience that every day when we are on the highway and someone slams on the brake. We generate a shock in a very simple way. General relativity is not like that. Perturbations propagate at the speed of light, regardless of the state of the field, regardless of the state of the gravity. And so, if shocks do not arise in general relativity in a way that doesn't follow, people were using, then phenomena like turbulence should not be there in gravity. But of course, they have nothing to do with each other. We can have shocks or not shocks, and turbulence can still be there. And so, this is an example of some work that we did some time ago, so, and then others as well. So this fluid gravity correspondence, let me just say a few words. If you follow this road that people like Shiraman, Mingwala, Veronica Hubney, and colleagues did, you put this assumption into Einstein's equations under the assumption that you have a negative cosmological constant, and you carry this perturbation under the assumption that it's a gradient expansion. Then you take the solutions, project them onto the ADS boundary, and what you find is that there is a way to identify natural variables of your gravity in terms of things, geometrical things that you can construct in the boundary, that now, after giving some names to it, you can make it look like a stationary tensor. For instance, if you just keep the leading order of these variables, then one can recognize that asymptotically, there is something called a stationary tensor that in geometrical terms has to do with the extrinsic curvature of this boundary. But in terms of this definition, well, you have some density, some pressure, some velocity, and some metric. In this case was flat metric. You can keep going. You can go to the first order gradients of these, and then here something shows up which has the shear, let me call it shear, associated with the u, velocity. You can go to the next order, and where you're going to have now second derivatives with many coefficients. And then you can say, well, what happens if we contrast this, which is things that you get purely from geometrical considerations? I stress, this is just a relabeling of things you knew from geometry. Particularly, you can open Landau-Lifshitz, and one by one, there is an exact coincidence. In fact, not so much. There were two extra terms here that are not in Landau-Lifshitz, but upon revision, Landau-Lifshitz makes some simplifying assumption that makes two terms drop, which are exactly the two terms that were here. But so now we established gravity here at the boundary is nothing but hydrodynamics, all the way to second order that people have computed. Furthermore, the structure of the equations here in characteristic variables, so you have the black hole here, are such that whatever feature you have in the boundary gets kind of transported rather trivially as far as structure is concerned inward. So if you have something that looks like a vortex here, all through, you will have the same structure. Rob Myers insisted that I call this like Sharknado, but I haven't watched the movie, nor I think I will ever do. But this is what we did. So with these colleagues, what you can do, as I said, you can study now only the boundary theory, which is a hydrodynamic theory with some particular equation of state that is dictated by the duality. You evolve it, and as I said, a very easy iteration inwards will generate the full solution. And so here is what one gets if you only iterate the hydro and you say just plot the vorticity of the field versus time as you go along here. You can all the way compute inside the solutions, and you can ask how close is my Ricci tensor to satisfy Einstein's equation, and it does it in quite a high accuracy value.
What about 3 dimensions and the boundary is 2D? Something should go wrong. Right?
This is 3 plus, here we're doing 3 plus 1 gravity, 2 plus 1 boundary ADS. I don't know, people have done that, but then black holes are fake black holes. They're in 2 plus 1 inside, right? So I don't know about that. My world, I said, my world doesn't have a negative cosmological constant, and I live in 3 plus 1 dimension. The rest are nice tools to calculate. I just try to keep myself grounded in what I see outside as much as I can.
So, but the ADS feature is unimportant, or?
My goal is to throw it away.
Okay.
So I'm building from IDS, but all through, I have, well, let me tell you what my gut feeling is from the very beginning. As in, my gut feeling is there's something interesting. All these features are driven by nonlinearities. Nonlinearities are seated here. Let me just put it this way. Nonlinearities sit there, not here. So all through, my gut tells me this will have an impact, but it's not crucial as far as the nonlinear content. Will determine timescales for sure, but not as far as this. But yes, so I'm just trying to argue. So here, as I said, oh, now this doesn't work. Okay, this is a simulation that is only hydro on the boundary. You wait long enough and you just take a snapshot at some time. This is work by Paul Chesler and collaborators at MIT at that time, where they took the same initial data, but they didn't evolve the hydro, they evolved the gravity. They then compute things on the boundary and say, let's compare. The funny thing here is that in some sense, these, these are all relativists by trade that were kind of buying the field theory argument, and these are field theory people buying the gravity argument. So we met each other coming from both opposite directions. Again, but now I'm trying to get rid of the negative cosmological constant. So now, believing that this is there, what can we do? And why haven't we not seen it before? Because, okay, I argue the nonlinears are there, they have this behavior. I just said the negative cosmological constant is there to do something, but the nonlinears are here. We should be able to go to a black hole in asymptotic flat spacetime and argue that a phenomenon like this is actually happening. So I'll tell you what we did. So imagine the following. I'm going to describe with a simple example. Now that, suppose, what's a nice lake around here? So suppose you have a lake. Again, this is a very silly example. And I'm here. I throw a rock here, and it generates waves. And it's a small rock. So it's a linear perturbation on the surface of the fluid. Now, I'm going to throw a second rock. If the viscosity of this fluid, in this case is water, is not too high, when it falls on a surface that has oscillations. So what is the right calculation to do? Is the right calculation to do, say, whatever the surface of the fluid description of the water is whatever was the background, and then I have the effects of perturbation 1 and the effects of perturbation 2? Or I should really consider that the background is a combination of the standard fluid with the oscillation and the time where the second rock falls in. So we're going to do this calculation. The typical calculation in gravity would have said every single perturbation is independent of each other. I want to capture what happens if they are going to talk to each other. So that's a simplistic picture to say we're going to come in here. We're going to assume this is the case. Solve for what the behavior of this solution is going to be. And I already said it's quasi-normal mode. So the space-time is now a space-time that is changing, has a mass and spin, but it's slowly changing because there is this perturbation that is behaving there. And then, to the simplistic calculation, I'm going to throw a scalar field in, which satisfies this equation. But this is the box of the combination of G kerr plus the quasi-normal mode. So this has in it some time and space dependence. And when you carry this equation through, you see that there is a potential parametric coupling between modes of the scalar field with modes of the background that is now slowly varying. And again, I'm not going to go through all the details, but you can see that some modes, depending on the amplitude of the initial perturbation, are such that we lose energy and will feed the scalar field, and as a consequence, the scalar field for a short time will grow exponentially. So this is a direct coupling of some modes into another, and this is what this picture is showing, that for a little time, some modes grow at the expense of the main mode. You can even get carried away, believe in this. Okay, at some point, we have to really drink our Kool-Aid. The criteria is the size of the perturbation, the first perturbation. Oh, it went. Wait. Okay, let me just go. The size of the perturbation H0, that was my first rock, divided by the azimuthal number. So an azimuthal number, so if I have a circle, sorry if I'm being too verbose here, this is my azimuthal number, it's something like that. So it looks like the inverse of a wavelength. Divided by the rate of change of the rate of decay of the main mode. So this is kind of akin to my viscosity. It wants to kind of disappear. It wants to go back to the flat surface of my pond. And so now we can use fluid language for a little bit to try and see what we get. So the size of the perturbation, let's call it V. 1/m, let's call it lambda, which is the wavelength. And the way of decay, let's call it viscosity over rho. And so the left quantity is exactly what we would call Reynolds number in fluid dynamics. Furthermore, if you actually look, what are the modes that receive energy are the modes that have longer wavelengths. So it really wants to say that these modes that preferentially will take energy to grow are the ones that have higher wavelength. So again, this is kind of pointing towards energy flowing to the IR, not to the UV. And there is a very beautiful paper recently called Extremal Black Hole Weather by Giuliano and collaborators, where they kind of took this idea, but then carried it all forward. So they dropped all the simplifications we did. The first one is they're not going to use a scatter field. They'll use a bona fide metric perturbation. It's more general than that. They're going to say all the orders are going to be carried out and thrown in as an H. And then they're going to use a 2-time scale expansion to keep track of what is the energy and what modes are moving in which way. And again, sparing you the details, let me give you the punchline. The punchline is such that if you kick a black hole, and it's why do they call it extremal black, or that's a typo, should be extremal black hole weather. They call it extremal black hole weather because the black hole they're thinking about to do this calculation is extremely spinning, a very rapidly spinning black hole. Why did they do that? For the same reasons we did in our calculation. The larger the spin, the slower the decay of these quasi-normal modes. It's said in a different term, the longer the perturbation is going to live. And if there is nonlinearity is going to do something, you actually want your signal to be there for as long as possible. So the higher the spin, the more the perturbations are going to linger there. So when they do that, they find out that after kicking the black holes and waiting for some time to a sort of steady state to appear, the amplitude of each individual modes, L being the angular momentum number, is of the form L to the -7/2. So if I have CL here versus L, it's something like that. And because it's this slope as opposed to that slope, and the slope is not too shallow, it also is pointing that energy has been essentially moved to the IR. And if I were to say one thing at this point, this is why I believe these waveforms are so simple. This is kind of the conjecture. They are so simple because we're doing gravity in 3+1 dimension. Hidden in this is a connection with 2+1 hydrodynamics. And 2+1 hydrodynamics have these quantities, which we have yet to recognize what they are in gravity. And some people are actively working on them, me being one of them, but I have been failing for the past, 15 years. I think my conjecture, or the first time I said that was 15 years ago. I still don't know what the entropy analog in gravity is.
So the cascade going to infrared and UV, the statement is that in 2+1, the energy goes to the infrared, right?
Let me be sharper than that.
3+1,
that's what I'm saying, but I'm actually pushing a little bit the envelope. The statement is the following. So suppose 3+1 or above, let's say greater or equal 3+1. Suppose you feed this energy, this wave number, then the energy will do that. And of course, if you are in Navier-Stokes, there is a famous Kolmogorov scaling of the energy per wave number. In relativity, we don't have this number, right? Because we don't have L and M being different units, but there is a family of numbers, and when people go and look for it, seems to be there, but of course, who knows? There might be a selection bias there. But let's say this is what you know in 3 plus 1. Now in 2 plus 1, if you do exactly the same exercise, you put energy there, the minus 5/3 lies there. And it's not that here is nothing, but it's a much steeper one. It's the minus 3. And this is the one that is governed by the entropy. So entropy governs that towards the UV is little energy, and most of it goes to the IR, towards the IR. So that's a statement that we know in hydrodynamics, in Navier-Stokes.
But wasn't there a statement about if I start with some chaotic perturbation in a fluid, that those modes want to go to UV modes or IR modes, and there was a transition. I forgot what it was, 2 dimensions or 3 dimensions. Isn't it true?
That I mean, it could be, but I mean, if you're in 3 plus 1 dimension, again, depends on
weather is complicated.
the aspect ratio
2D.
in these versus the R2. But then there is a Reynolds number. Are you thinking about Reynolds number?
Maybe it's 1 plus 1. Maybe 2 dimensions. It's when.
So there's a weak turbulence cascade there. And you're thinking about the instability of ADS, perhaps?
No, forget about it yet.
Okay.
I'm just thinking that fluids, I thought turbulence in fluids, but maybe it was many years ago. I thought turbulence in fluids had a distinct feature depending on the number of dimensions. In some dimensions, when things become chaotic at some length scale, they tend to go to create chaotic behavior at lower and lower scales. And in some other dimensions, it was higher and higher scales.
Well, but that might be 2 plus 1 versus 3 plus 1.
Okay.
I mean, that's what I'm saying happens in 2 plus 1 versus 3 plus 1.
Okay, good, good.
Or n plus 1, but where only 2 dimensions are the most relevant. But if you have much longer wavelengths in the other n minus 2 dimensions, but in the 2, that's where you're kind of hitting the turbulence.
Okay, okay.
Then it's going to trigger one way or another.
And then, so that means that 2 plus 1 and 3 plus 1 turbulence is very, very different, right, from
Yes.
that behavior? So that should translate in ADS into some ADS4 versus ADS5 being super different, right?
The nonlinear behavior, yes.
I see. And is this something easy to explain? Why we
Yeah,
are in ADS4 or ADS5?
yeah, it's a
is very
topological invariance. So you can also just go to the hydro. And the hydro, so this entropy has to do with the conservation of the square of the vorticity.
Okay.
And a vortex in 2 plus 1, you cannot tumble, right? There is nothing it can do. Like there is not a place where it can go to, but in 3 plus 1, it can do everything. So then you lose control. Okay, so let's see. Let me just say a few things about Caroline hydrodynamics, and I'm way out of time, so just maybe I'll stop at some point. So what is this Caroline hydrodynamics? Have people heard about that? Yeah? Does anyone care? Yeah, C goes to 0, but why? So, yeah, so if you take the Galilean group and take C to infinity, you have the standard one, and then the Lorentzian goes to Galilean, but if you do the other one, you have this other group, which is called the group of Carroll. So if you take the conservation of stress in a tensor, and you take that limit, you start with relativistic hydrodynamics, you take the limit, you get to Navier-Stokes, everything is fine. But if you take the opposite limit, several weird things happen. In particular, you have a double number of equations, because there is something that goes to 0 naturally by virtue of, why is it sometimes this work and sometimes it, well, and now it goes this way. Okay, so there are some things that naturally go to 0, so you take the limit, and there is a term that has to go to 0 by its own, as independently of another one that is going as 1 over c squared. So you end up with some hydrodynamics that has double the number of equations. That's in general. And it just so happened that if we go back to those weird-looking equations, which were the equations of the Einstein's equations, that were projected onto a null surface here, which may be the horizon or maybe any general surface, the two equations that you had here were, like if this is a tangent to the generator of the horizon, where the Einstein tensor, let's say, or the Ricci foreign vacuum, LL, so we project this one onto both LL, or LA. This is what we call Wright-Choudhury, and I'm going to not there writing now. And this is what people call Damour equation. But it just has so happen to be the subset of the Caroline hydrodynamic equations. So a subset of the Carolian relativity, Carolian hydrodynamic equations is precisely these null surface equations that people have been struggling with in the past. And here I'm just showing or flashing them. They are highly unnatural in many respects, but they have to be unnatural. This Carolian thing just closed the cones. And so it's not surprising that we end up with a structure that we're not naturally familiar with. And one simple question that one would like to answer is, how would this fluid thermalize? How would this fluid reach equilibrium if it's not talking with its nearest neighbors? In the standard fluid picture, right, we have things that are moving around, hitting each other, there is shear. There is the communication between what I'm doing and what my nearest neighbor is doing is crucial in achieving this thermalization or this equilibration. And so this is what people struggle with or work with in this context. But if one says, well, let's just look at the subset that is dual to the Einstein equations, well, the picture is a bit more clear. So the equations of motion, this is precisely the equation I said. This is the Raychaudhuri equation, and this is the Damour equation in terms of this weird vector on the null generators that kind of parameterize potential rotations of my generators. Again, this is not a type of equation that one can look in isolation and understand what's going to happen, but in particular because it has pieces like the intrinsic metric, the intrinsic curvature of the surface gravity, of the null surface, and it has pieces that actually, in this picture, have to do with maybe radiation or perturbations that are about to cross the horizon. And so one thing we could do is just go back to the perturbation scheme, think about these ways, and then try to see if one can incorporate the effect of the bulk onto the behavior of the surface and maybe clarify the picture. So this is what we've done recently. Yeah.
Infinity is a non-relativistic limit, so it's very easy to get an intuition. C to 0, what is it physically?
You close the cones.
Yeah.
So now particles are essentially staying in place and not talking with each other. And the only thing that subsists in that picture are things that move at the speed of light. Anything that moves slower than that gets discarded or gets thrown away.
Is there any situation in physics? And then we do an expansion around that limit, right?
Well, is there any situation?
For example, when a jet goes much faster than the speed of sound, does the fluid around the jet become Carolian and then...
Well, no, here what we say is that the null generators of a null surface are Carolian.
No, but more physical. I mean, is there some fluid in nature that
No,
I
right?
care about the Carolian limit? No?
No, you would say maybe a fluid made of photons. That any null fluid would be that. Because the only, and then whether you close it or not doesn't matter. It's just a parameter. They just follow it.
I see. So a fluid much bigger than the speed of sound is not the same thing because sound is not light.
Sound is not
It's
light.
important to be relativistic. Okay.
Yeah.
Moving at the speed of light, and that's a strong restriction.
I see. But does it ever happen in some situation in nature?
I don't think,
With like two stars very fast going at each other?
well, the null surface describing the horizon. So I'm going back to that. I mean, just whatever is made out of things that move at the speed of light.
So you keep the laws of special.
Speed of light there, it's much smaller.
I don't know.
So you keep special relativity. So nothing can travel faster than the speed of light, and you take the speed of light to 0.
The speed of light to infinity. So zero.
So nothing propagates.
Exactly.
So two points which aren't at the same point don't talk to each other.
That's right. And how would this fluid
Why is that
thermalize?
useful?
I have no clue. This is why mathematicians, when they go rampant,
Okay.
but okay, so now, okay, just because we're about to close, let me just say a few general things. So if you take the geometry pictures, and I said, now I'm not going to look at all the high Carolian fluids, but a subset of Carolian fluids, and is dual to the horizon behavior on null surface, how does that fluid thermalize? In the concept of gravity, it's the same question as saying, how would the null surface know that it's going to be a horizon in the future? It will depend on how much energy crosses in, etc. But, okay, let's imagine that we have this fluid, Okay, we're going to do this experiment. I'm going to chop the fluid in two. I'm going to give it a temperature, 1 to the left-hand side, 2 to the right-hand side, and they cannot talk to each other. How is it going to thermalize? Well, one way that can thermalize is that it will deform, let's say T1 is hot, T2 is cold. T1 will deform my cup more than the T2. And then the energy density in one side will get lower than the other one, and that's how they will thermalize. So the dual to the Carolean fluid on the gravity, translated into gravity terms, that's what they do. So when I say the fluid, the Carolean fluids are dual to the gravity fluids, for instance, we're saying that the expansion theta is playing the role of the internal energy of the fluid, but also it's playing the role of how large the fluid, where is it going to. And so one can also do a similar picture with the Haji check. So that's something we have put out there. I promise if you do this, carry these perturbations and then include the back reaction of what's going on in the bulk, you can write the equations in a cleaner way. And indeed, you end up with something that looks, again, very much like an equation where there is a fight between dissipative contributions and nonlinear interactions. Okay, let me just jump over that. Let me just, maybe I'll say one last thing about the fluid gravity correspondence. I think I've said this in the past, but this is because it connects back to Brazil in a very significant manner. When you write, and I erase it, when I write the relativistic fluid dynamics in this way, I said that one has TAB, let's say, oops. We have the perfect fluid contribution, we have shear here, let's say, and then we have second derivatives of fluid. So now let's do mathematics, PDE. If I just think of the equation of motion that I get from here, these are nicely hyperbolic. We understand them, and everything is fine. I'm talking relativistic fluid dynamics. If I include this term, we're bad. This is an equation of motion that describes there are tachyons, there's propagation faster than light. Nothing works here. I mean, not that nothing works, but I mean, lots of things can go very wrong. And it's worse if you add this. So a long time ago, people recognized that and said, well, we need to fix this. You can kind of hand wave. This has to do with the fact that we're using a particular averaging in a regime that where the constituents are moving not in the right way. And one can make all sorts of arguments, but these are the equations. So Israel and Stewart postulated a way to fix it. So they said, well, the problems that arise here arise in the UV, and the UV is problematic. It's not within the context where you could have written this, so fix it this way. And there's a theorem that says you only have a chance to fix it if you go all the way to second order. This is an honest-to-God theorem proven by Bob Geroch a long time ago, and great. But here come some fellow countrymen of yours, Benfica, Noronha, and Visconsi. I don't know if you know them. But they said, we have a way to write things up to here. Okay, they put in between quotes. So now that's gone. Where the mathematical equations are not sound. How in the world did they get that when there was a theorem? They get it because they are going to, in the previous cases, one imposition was that the entropy current was such that it was never decreasing. They relaxed that. They said, well, we're going to allow it to be decreasing in terms of our higher order in the gradient expansion, and we're fine. And that's fine, because after all, either you claim it here or you claim it there, at some point it's going to go. So they have a much simpler formulation, and this is being used. But the reason I say this is, remember I said, well, in fluid gravity correspondence, we're going back to the context of ADS, Shiraming, Walla, and companies, Cubney, Rangamani. They took the Einstein's equations, they projected there in the gradient expansion, and they got this. This is what it said. And so the question we asked, we look at Ciambelli, who I think is going to visit sometime in the future. Okay. We ask, can we go here again? And is it something that was left out that could accommodate this formulation? Because another thing that happens here, this is something that the formulation comes in the so-called Landau frame. Okay, that's a special frame. I said, what forced the Landau frame? And it turns out that in this solution here, there are some homogeneous solutions that you have to fix somehow, and they fix it such that when they did the translation to the fluid language, they were in the Landau frame. But then you can relax that. If you relax that, then in principle, you can accommodate their formulation. All so far, so good. There was no surprise here. But what we say is that, is there a way to ask something that will fix the frame in some particular way that is purely geometrical related to the horizon itself? So you can ask, my null generator, where it's in equilibrium or is perturbed, is such that they are the same, let's say. That could be one option that you could choose to. You can also choose that, I don't know, the surface gravity K in equilibrium be the same one when you perturb it to linear order. So suppose you impose that. What are the consequences? The consequences are here, you end up in BD and K. And so when I said the other day in lunch, there are some things that I think are interesting, but I don't have an answer yet. I don't have an answer why a geometrical requirement here will fix or will take us to the Benfica, Disconsignaronia, and Compton formulation. And I just think it speaks for some deeper hidden connection between these two camps that we have yet to understand. I don't know. I don't know why it came out to be, but it did. So I think at this point I'll stop here. Thank you.
So I had one question. So people like Unruh and followers of him think you can study black holes by studying water waves.
Yeah.
Is that unrelated to this or related or?
I think it's unrelated.
Okay, that's what I thought.
It's an interesting, it depends also what you want to study. These black hole analogs are good at for making some connections, but I think it has nothing, well, at
Not
face value,
obvious.
doesn't have anything to do with it.
Other question? Rogério?
Is there a version of this in Young Mills instead of gravity?
I don't know.
People often, or recently, sometimes they write solutions of gravity and they write in this double copy that some solutions can be written as, so maybe there is some square root of the fluid, some problem.
I don't know.
Which
It's an
one?
interesting left field question, but I don't have any clue.
So let's thank Luis again. Okay, I can ask the question later. I need to go.